Hello again, this is Harry Lythall here at SM0VPO. Now in this video I'll try to answer the question, what is RF? But I'll just give a basic rudimentary description. But I'll begin this video with an email comment from a viewer. Watch the video, quality of video. But why are you concentrating on ancient technology that is not relevant today? Other than a few hobby radio enthusiasts, does anyone actually use radio today? I speak to people every day without using radio. I use my mobile telephone. I listen to radio, it's DAB, that is digital and not your old-fashioned analogue radio. Even my TV set has digital channels. It would be good if you could explain more about digital antennas and communications. This email was interesting as I've heard similar comments from several people before, mainly younger people. Now, radio communications are all analogue. Your mobile phone uses radio frequencies to transmit your voice to a radio base station without wires. And that's why it's mobile. Your Bluetooth headset uses radio. Radio technology is baked into nearly everything these days, but high-level users often forget what is behind modern equipment. I mean, for example, the wheel was invented, 40,000 years ago? But we still use cars, buses and trains, but they still use wheels. So back to the question, what is RF? RF is simply an abbreviation for radio frequency, and it refers to energy that is alternating in exactly the same stuff that comes out of the power sockets in your house and heats up the water in your electric kettle. The only difference is the frequency, how it behaves, and how it is used. The three basic measurements are frequency, wavelength, and amplitude. To measure frequency, you just count the number of cycles in 1 second. It's as simple as that, nothing complicated, there's no rocket science. Now if you look at a sine wave, then you can see the cycles on an oscilloscope as they progress through time from left to the right of the screen. Using an oscilloscope you can read the voltage, you can read the approximate frequency. But that is about all. Here is 50 cycles per second, or 50 Hertz, viewed on an oscilloscope. Today, cycles per second are called Hertz, after the German physicist Heinrich Hertz, who discovered radio waves. Down here is 50 million Hertz, or 50 megahertz, viewed on the same oscilloscope. Can you see the difference? Only the numbers are different. RF is accepted to be any frequency greater than about 3 kilohertz. Wavelength. Light and radio waves travel at 300 million meters per second. Now I want you for a moment to imagine a single pulse or a click transmitted from an antenna which travels at the speed of light. So after 1 second, that click will have travelled 300 million meters. Now if you transmit 1 million clicks in 1 second, then the distance between each successive click will only be 300 meters. This distance is the wavelength. As the frequency increases, so the wavelength decreases. Early radio receivers were calibrated in wavelength, but today they're calibrated in megahertz. An antenna must be the correct length to work, and this is related to the wavelength. Now, a classic horizontal half-wave dipole antenna for 50 Hertz would be 3,000 kilometers long and should be supported on a mast that's 1,500 kilometers high in space. This is clearly impractical. The frequency is also too low to carry any meaningful information. 10 kilohertz and below has been used to communicate with submarines. The frequencies are so low that they can penetrate water. A half-wave dipole for 10 kHz should be 15 kilometers long, but there are RF tricks that can be used to reduce the physical length. One of the first antennas for submarine communications was erected between the peaks of two mountains. A half-wave dipole for our 50 megahertz here is only 3 meters long. Amplitude is very similar to the strength of a signal, and this can be measured in volts, or watts if you're talking about RF power levels. Radio signals received by a mobile phone can be in millivolts, or even microvolts. And today we measure transmitter signals in dBW, that's decibels referred to 1 watt. We usually measure signal path losses through the air in dB, decibels, which is just a loss figure not related to anything, or in dBm, that is decibels related to 1 milliwatt. Decibels are bells multiplied by 10, so they're more convenient, named after Alexander Bell, the inventor of the telephone. 1 bell or plus 10 dB means 10 times more power than something. 20 dBs is 100 times more, and so on. So plus 20 dBm means 100 times 1 milliwatt. And it's based on the same logarithms you used to look up when you were at school. At least I did when I went to school. You can, by the way, download an old application called WinScope, and you can run it on your modern PC, and it will turn your computer into a cost-free oscilloscope that can measure up to about 20 kilohertz from the microphone input of the computer. But it has got very simple functions. I use WinScope to debug PIC microprocessors when I'm programming them, and I use it on the same computer for programming. While the oscilloscope measures low frequencies in the time domain, the spectrum analyzer measures frequencies in the frequency domain. The lowest frequencies are to the left of the screen, and the higher frequencies are to the right of the display. So you have a panorama. The vertical axis shows the amplitude of the signal. The spectrum analyzer can measure frequencies well into the VHF and the UHF spectrums, and even beyond. And they can also display micro distortion at a very low level. And this is very important when you're testing, for example, transmitters. Our 50 megahertz signal looks nice and clean on the oscilloscope, but the spectrum analyzer shows a very different picture. Here you can see that there are second, third, fourth and fifth harmonics of that carrier. So these are at 100, 150 and 200 megahertz and so on, right at the band. This would be considered a dirty transmitter that could cause interference to other radio services. OK, now let's look at off the air from an antenna of the FM broadcast band from 88 to 108 megahertz. Here you see all the FM radio stations around Stockholm. But I'll just zoom in on one radio station, and I've chosen Sweden's P1 on 103.3. See how the signal varies on the analyzer in sympathy with the sound you are hearing on this transistor radio. This variation of the signals is called modulation. Now, 30 years ago, an analyzer like this could cost 20 times more than it does today. But now it is only about, what, $2,000 for a modest instrument for hobby use. OK, I use that term modulation. Now, modulation is actually controlled distortion of the radio signal so that it can be used to carry intelligence. Here you can see modulation on the oscilloscope and the analyzer. You cannot hear a radio signal, so that controlled distortion can be speech, music, or even digital data. And there are basically 3 different types of modulation. This is how they look on the oscilloscope when I switch the modulation on and off. amplitude modulation, AM, where the amplitude of the power is varied in sympathy with the sound or even digital data. Frequency modulation, or FM, where the frequency of the carrier it varies in sympathy with the sound or data. This is phase modulation, where the carrier frequency is constant, but the phase of the waveform can be changed or switched to carry sound or data. Here I've modulated it with a square wave so that you can easily see the phase switching points. Amplitude modulation was the earliest form of audio modulation, and it's really wasteful. For example, a 100-watt transmitter at 100% modulation will have a total power of 150 watts, 100 plus 50 in the sidebands. The 100 watts is the carrier, which is actually wasted power. All the intelligence is in the 50 watts in two sidebands. The two sidebands carry duplicate information, so really the intelligence is all contained in just 25 watts for 150 watts of total radio power. That's a waste. Many radio enthusiasts today use radios that remove the carrier and one redundant sideband, leaving just the 17% of that signal that is actually needed. Also, some of these modulation techniques can be compounded. For example, a stereo FM transmission modulation contains a 38 kHz based AM carrier that is used to encode a stereo channel information. AM, FM and single sideband transmissions can be used to carry two audio tones switched to send audio frequency shift keying. This sort of thing was used in the 1900s to send teleprinter information. Now, the earliest modulation was simply on-off keying used to send Morse code. There are many other forms of modulation, but most are variations of AM, FM and PM. Your mobile phone digitizes your voice into strings of noughts and ones, and some of these bits of data will change the amplitude of the RF carrier. Other bits may change the phase of the same RF carrier so that two bits of data are transmitted simultaneously on one carrier, and this also happens many thousands of times a second. And this is called quadrature amplitude modulation, or QAM. Radio engineers do like these abbreviations. We can also transmit not one but many carrier frequencies simultaneously, typically 2,400 or more for LTE, each carrying 2,000 or more bits per second. And this way you can send many millions of data bits per second to get mobile broadband. Your mobile phone sends and receives analog RF carrying high-speed digital data so that you can watch your YouTube videos and even this video on your mobile phone. RF is also used to transfer digitized sound from your telephone to your Bluetooth headphone and connect to the Wi-Fi via radio. These are all just low-power radio transmissions. Other forms of radio transmissions are GPS for navigation and the Internet of Things. But RF is everywhere, but it's not always obvious that it is there. So let's have a brief recap. In this video I talked about what radio signals are. I showed an oscilloscope displaying waveforms, frequencies and voltages. You saw my Spectrum Analyser and a display of the FM band. I also explained some basic modulation methods and how they can be used. Well, I hope that you found all this interesting. There will be more videos to come, for example, antennas, radio components and their uses, RF safety, and maybe even debunking some RF myths and conspiracy theories. If you have got any constructive suggestions, then please feel free to leave comments below and also push a few buttons. I also have a forum where you can ask questions to me and other experienced radio enthusiasts. So, I want to thank you very much for listening to me once again. You will no doubt see me again soon discussing antennas and other radio topics. So I wish you all the very best regards from myself, Harry Lythall, SM0VPO, an Englishman in Sweden.